Okay, cool. We'll go ahead and get started. So hi, everyone. Thank you all so much for joining the student research competition. This is the first time Sigmetrics hosts one of these. And this is an event that is sponsored by Microsoft Research and ACM. And it's a venue for students, both graduate and undergraduate, to first present posters, which happened on Tuesday. There was a poster presentation. And these are the finals, which are oral presentations by the student finalists from the poster session. So this is a competition for single author papers and posters. And there are cash prizes, which the students are competing for today. So we're going to go through each of our finalists. We have one undergraduate finalist and 3 graduate finalists. Each of the presentations will be 10 minutes with 2 minutes for Q&A. And then at the end, we have a panel of judges who will convene and decide on the winners. So I want to very quickly introduce, hold on, do we have Tianyin? Oh yeah, Tianyin's in. Okay, we have a panel of 5 judges. Now everyone's joined. So I'm going to very quickly introduce all of them. We have Weina Wang from CMU. We have Shailesh Venkatakrishnan from OSU. We have Nicholas Gast from INRIA, and we have Tianyin Xu from UIUC. So huge thank you to our judges for taking the time to help review the submissions, review the posters on Tuesday, and review the presentations today. All right, so let's get started. Our first presenter today is going to be Edwin Peng from the undergraduate category. So Edwin, please take it away.
Hello, can you see the slides? Okay, yeah. So, my name is Edwin. I'm an undergraduate at Carnegie Mellon studying math and computer science. And today I'm going to talk about my research project, which focuses on queuing systems with preemption costs. And for this project, I was advised by Zeev Scully and Maura Harko-Bolter, both at CMU. So why do we care about this? Or like, what is the motivation behind this research? Well, the idea is preemption is practically important in queuing systems. For example, there's class-based priority systems where you can just have like 10 classes and classes have priority in order, or there's size-based priority, which is a scheduling policy such as FB or SRPT, which is good for low mean response time. And there's other priority systems, but these are typically good to study. So there's plenty of queuing theory that studies preemptive scheduling. For example, the SOAP paper written by Zeev studies all size-based priority systems in some generality and is able to give good analysis. But the issue is that in practice, almost all preemption takes time. For example, you can imagine a computer switching between 2 jobs or like having to do this multiple times. You couldn't really imagine that it would happen instantaneously. So almost all theory does not account for this practical preemption cost, so which is very important. So what is the model? The model is an MG1, the general distribution, preemptive priority queue with switching overhead. So as you can see in this very simple picture, there's 2 classes. There's class 1 jobs, some arrival rate, some size distribution, class 2 jobs. And as you can see in the model, the class 1 jobs have priority over the class 2 jobs. So the presentation in the model and the presentation will go over a 2-class system because it's easy to draw and easy to visualize, but the system works in the analysis works in general for any number of classes. So what is the preemption model? So first of all, when a class 1 job arrives when a class 2 job is in service, there's a pause. The pause has size distribution C2, where we write C2 because we can have, in a multi-class system, we can have a separate pause distribution for each class. The pauses are generally distributed, and the intuition is, for example, like if you're in a system or if you're playing a game or something, when you want to save progress on a job, it takes some time. And so the dual of that is after you're done with all the higher priority work, you want to go back to your low priority job. And when you resume to it, there's a resume with size distributed D2, a separate general distribution. And the intuition is when you want to get back to it, take some time to reload your progress. So I'm going to walk you through an example of what happens at the system when a preemption occurs, just to visualize what this analysis will go over. And maybe like, what's so hard about it? So at the start of our analysis, there's low priority job, it's just in service, and all of a sudden a higher priority job arrives. So according to the preemption model, we have to pause, and this incurs some switching work. So there's some switching work, and then we do the higher priority work. And then once there's no more higher priority work in the system, we go back to, well, we have to reload our progress. So there's this resume period, but a variety of things can happen in this resume period. And the most significant thing that could happen in this resume period is a class 1 job could arrive. And what happens when a class 1 job arrives is at the end of the switching period, there is now a class 1 job in the system. So we can't really resume to our job because it's no longer the highest priority job in the system. So in our model, once it arrives, we still finish the resume period, and we say it fails because the class 1 job arrived during it. So we pause the job again, do some more work, and then try to resume again. And let's just say this time no class 1 job arrives, so we say it succeeds. So we go back to working on a lower priority job. This is just an example of what happens, or like what could happen when a preemption occurs. And the issue is that because of these failures and succeeds, it's pretty hard to analyze. So what are our contributions? Well, we are able to develop a new technique to analyze system switching overhead and analyze the issue with the fails and resumes described before. And we're able to come up with a formula, exact formula for each class's mean response time in a preemptive priority system with switching overhead. So as we saw previously, the main obstacle in our analysis is that the busy period length is hard to analyze because it's not just a standard busy period and a lot of different things can happen during it. So, I mean, the idea, classic MG1 busy period is that you can reorder jobs however you want. And then, so the length of a busy period is just usually some linear function in terms of what started the busy period. But the issue in our system is reordering jobs can change which overheads happen. And you can imagine, maybe this is not so obvious, but it's like if you change the order in which jobs are done when there's preemption, like the preemptions will change, so the overheads will happen. And that makes the busy period hard to analyze. But a solution for this that we were able to come up with is we're able to quote unquote accumulate overhead work for later. And what that means is as the preemptions arrive, maybe we don't do them immediately, but we keep track of all the preemption costs and all the preemption periods that have arrived. And it turns out that when you're able to do, after doing this, you can now reorder work. And how this can be helpful, you can imagine like you're doing a low priority job and then a class 1 job arrives. This causes a preemption, but if we're able to reorder work, we can just say, oh, let's just finish the low priority job and then do the preemption afterwards. And you can imagine that that would be a lot easier to analyze. So in summary, the problem is that practical systems have switching overhead, but switching overhead is not very present in theory. And so the solution is we introduced the MG1 model with switching overhead and came up with an exact mean response time formula for each class. And the key idea we used was this overhead busy period analysis. So this is our theorem. It's a lot of letters, you don't have to read it. And then, so some questions you might have is like, well, it says in the solution that we introduced a very exact model and came up with only mean response time. So how is this helpful? Well, we think that the analysis can be extended to other overhead models. For example, in our model, we had pauses, which couldn't be interrupted, obviously, and resumes, which couldn't be interrupted. But you can imagine a system where as soon as a higher class arrival happens during a resume period, the resume period immediately stops instead of ending after it's done and then doing a pause. So that's another type of system we can analyze. And something else is different priority schedules. So here we had class-based preemptive priority, but you can imagine this working on some sort of SRPT where you have buckets for different job sizes or something like that. So yeah, that's about it. Oh, wait, I don't need this slide. I guess that's it.
Okay, thank you, Edwin.
Uh-huh.
Are there any questions? Nicola, go ahead and ask your question.
Hello. I'm just wondering here, so you're studying the general MG1 model, and I'm wondering if there's been some work before on like exponential job sizes, because I imagine it's quite much simpler. And if yes, then like what's the fundamental difference between the two results?
On exponential job sizes?
Yeah.
I'm not sure about previous work on exponential job sizes. I don't know if there's been work done, but I don't think so.
Okay.
Yeah, I'm not sure.
Okay, thank you.
Okay, we have a question from Tianyin. Do you want to go ahead?
Sure. Like, very nice work, Edwin. Like, I'm just curious. Like, have you applied like the new model like to any practical systems? And if so, what are the systems like you are targeting?
Practical systems?
Yeah, like you're basically like the model, like basically as you mentioned, like it can consider like the switching overhead, right? The context switch, and like improving like the scheduling. Like, so what are the systems like you are targeting, which can benefit from your work?
Well, I guess part of the issue, like as a whole, is like before, when you're thinking about maybe some better ways to schedule certain systems, there wasn't really a way to even, well, you can't analyze like which scheduling policy is better than which other one if you don't even have an analysis. And I guess this paper just creates an analysis in order to establish the mean response time. And an extension could be to apply it to practical systems, but we have not done that yet.
Sounds good. Thank you.
Okay, thanks. We have a question from the audience from Tuinangshu. Would you like to unmute yourself?
Yeah, am I audible?
Yep, we can hear you.
Yeah. Thanks, Edwin, for the talk. My question is, since like preemption is used to reduce response time of systems, and you have analyzed like what are the cost of preemptions, do you have an analysis of at what level the preemptions are bad? Like if you have a very high resume or pause cost, like what points do you have a switch that preemption is bad?
Well, like I said before, these are extensions that, well, I mean, if we have a formula for how long it takes, like it wouldn't be that hard to extend it to like, if you just plug in these numbers for like how often preemptions occur or like what type of preemptions you want to do, like you can just compare two variables or expressions and see if it's better or not, but I guess we have not done that yet, so.
Okay, thanks.
Yeah.
Okay, thank you very much. I think in the interest of time, let's move on to the next presentation. So thank you, Edwin. So our next presenter is going to be from the graduate category. This is Mashid Gassemi. So Mashid, could you share your slides?
Yeah, sure. All right. Hello, everyone. My name is Mahshid. I'm a PhD student at Columbia Department of Electrical Engineering. Today, I'm going to present an automated video-based social distancing analyzer called AutoSDA. Social distancing can reduce the infection rates in respiratory pandemics such as COVID-19, especially in dense urban areas. Even though in some areas the COVID vaccine is broadly available, there are still many places where most of the population is not vaccinated. Moreover, according to the expert, even a vaccinated person is still likely to get infected and transmit the infection to those who are not vaccinated. So it is still important to adhere to some preventive protocols such as physical distancing. Furthermore, the information about the compliance of the pedestrian with the pandemic restriction is critical in assessing and controlling the pandemic, as well as being well prepared for any potential similar pandemic in the future. Therefore, we use the Cosmos testbed infrastructure, which were opportunistically deployed before the pandemic to build the video analytic pipeline that evaluates the compliance of the pedestrian with social distancing policies. And we have a camera deployed on the second floor of the Columbia's Mod building, which is looking at the intersection of the Amsterdam Avenue and 120th Street. We use the recorded videos from this camera to evaluate how the COVID pandemic has impacted the pedestrians' behavior. First, I will introduce the AutoSDA pipeline and how it transforms an object detector and a tracker to a social distancing analyzer. And then I will describe the designed modules, which are multi-area calibration, ID correction, and group detection. At the end, I will present the result of applying AutoSDA on the recorded videos at Cosmos pilot site. AutoSDA pipeline consists of multiple modules. The calibration module converts the 2D on-image distances to 3D on-ground distances. The object detection and the tracking locates the pedestrians and assign an ID to each of them. The ID correction rectifies the output of the tracker and extracts the entire trajectory of each pedestrian. The group detection excludes those pedestrians in a single social group from the social distancing violation. So essentially in AutoSDA, we have designed the calibration, ID correction, and group detection modules to transform an off-the-shelf object detector and a tracker to a social distancing analyzer. And the result will be something like that, detecting the social group and the social distancing violation from the video. Intrinsic, focusing on the multi-area camera calibration module, intrinsic and extrinsic parameters of the cameras are required to convert 2D distances to 3D distances on the ground. Our measurements show that only one set of parameters for the whole scene of the camera will lead to inaccurate on-ground distance calculation. Therefore, in this AutoSDA, we split the scene of the camera to 10 areas, and we calculated the parameters for each area individually. These parameters are then used to compute the distance between each two pedestrians with less than 10 centimeters. The Cosmos cameras are located at a relatively high altitude and they have an oblique view of the intersection. Therefore, the pedestrians look small and their view might be blocked by the vehicles, traffic lights, and other pedestrians. This issue degrades the performance of the tracker. It means the tracker might assign multiple IDs to a single pedestrian. And the ID correction module will detect those IDs that belong to a single person. For example, in this picture that you see, if you consider these segments that belong to a single trajectory of this person, the ID correction can use the linear approximation of the tail of one of the segments and approximate the start point of the subsequent segment. And in case this approximation is a good approximation, it is likely that these two segments are belong to a single trajectory. To enhance the social distancing analysis, we designed a group detection algorithm to exclude the social groups from social distancing violation. And the off-the-shelf group detection methods are not applicable to our dataset and many realistic deployments because these methods require details such as head and body orientation, velocity, exact trajectory, etc. These details cannot be obtained from a camera in a high altitude at a corner of an intersection. Therefore, we design a group detection algorithm that detects the social groups with limited data that can be obtained from the Cosmos cameras. Essentially, the main idea of this group detection algorithm is to keep track of the distance between each two pedestrians, and the two pedestrians are announced to be in a single social group if these the three conditions hold. Average distance is less than a threshold. A standard deviation of the distance is also less than a specific threshold, and they are moving in the same direction. For example, in this video, we show the distance of two unaffiliated pedestrian, which shows like how it is fluctuating. And also in this next video, we are comparing this fluctuation of two pedestrian of a single group and two unaffiliated pedestrian, which are, you will see how fluctuating the unaffiliated pedestrian distances. We evaluated the impact of COVID-19 pandemic on pedestrians' behavior by applying AutoSDA to videos recording in 3 stages of time, which is pre-pandemic videos that were opportunistically recorded before the pandemic in June 2019, pandemic videos which are recorded in June, July 2020, which is basically soon after the lockdown, and also post-vaccine videos which are recorded in May 2020, which is after the availability of the vaccine in New York City. So in general, compared to prior work, as well as an object detector, AutoSDA uses a tracker to measure the duration of the social distancing violation incidents. Moreover, rather than a generic calibration method, we designed a calibration method that can compute the on-ground distance with high accuracy. AutoSDA is also equipped with correction and group detection module to further enhance the social distancing analysis. In contrast to prior work, we have used AutoSDA to perform an actual real-world COVID-19 pandemic impact analysis. So for example, in this plot, we compare the density of the pedestrian in 3 different stages of time. This illustrates how the density of pedestrian has decreased right after the lockdown in this one, and while it has slightly increased after the availability of the vaccine. And we also performed a measurement on the compliance of the pedestrian with social distancing policies. For example, in this plot, we show the percent of social distancing violators in pandemic videos and in post-vaccine videos. As you see, the distribution for the post-vaccine has slightly shifted to the right. We also have the same plot for the social distancing violation time and also maximum social distancing violation that was observed, that I'm going to skip because of the time. So also this is the result for the like different time of the day, which is, for example, if the percentage of social distancing violated, for example, for pandemic videos, if you look at 2 p.m., around 33% of pedestrians violate social distancing. However, for post-vaccine videos, this number grows to 54%. And the same things for the percentage of pedestrian affiliated with a social group for the pandemic and post-vaccine videos. You see how the number of social group is increasing after the availability of the vaccine. So in general, we designed 3 modules, which are multi-area calibration, ID correction, and group detection to transform an object detector and a tracker to a social distancing analyzer. The future work will include designing privacy preserving methods and integrating data from multiple cameras and also other type of sensor like LiDARs. And in general, AutoSDA is an initial step toward other use cases of Cosmos testbed, which could be a distributed edge cloud analytics, cloud connected autonomous vehicle, AR, VR edge cloud, etc. Thank you.
All right, thank you, Mashid. Do we have any questions? Wayna.
I think you used the ID correction algorithm and a group detection algorithm. So I was wondering, how did you evaluate the accuracies of those 2 algorithms?
Yeah, so basically one exact way of doing this will be having annotated videos and like multiple people doing this annotation. But however, because we didn't have that many data set and also like people doing annotation, what we did was to take sample videos and then running the algorithm on those sample videos and visually compare the number of actually, like for example, detected groups and like detected IDs and compare it with visual IDs and groups that we are seeing. That's how we evaluate.
For those sample videos, you know the underlying truth of the groups?
Yes, we just visually we can see, and yeah.
Okay, yeah.
Shailesh?
Hi, I have a question. So can you comment on the computational complexity of your algorithm? Like what I'm interested in is like, are you able to do these predictions in real time, or do you need to download the videos first and then do processing offline?
Okay, so basically, yes, this AutoSTA can be run in real time, like based on our measurements. So it can like go up to 30 frames per second. However, for example, let's if we consider this group detection, it will keep update the information. For example, once, for example, two pedestrians which belong to a social group enter the scene of the camera, it doesn't like say these are in a single social group, but it will keep track of their trajectory, and after like some time it will update the data. So it might be the case that two persons that are like very close to each other are walking very close to each other at the beginning, it will detect them as a like a group. However, after some time it will update and like detect them as unaffiliated pedestrian. So basically the pipeline can be run in real time, but some of the data needs some of the like modules need some time to update their information and get the like exact results.
Thank you.
Yeah.
Okay, one last question, Nicolas?
Yes, I had a question about the experiment that you showed us, like this. I think it's this video.
This one?
I think it's this one. So where I have the impression that the distance between the two people, distance is blue, is varying quite a lot. But you say that the accuracy is like less than 10 centimeters of errors. I'm wondering if, I mean, how did you evaluate this, and how confident are you in this, like 10 centimeters of errors?
Yeah, so basically for that, in order to measure the accuracy of this conversion, I went to this intersection and measured the distance of these zebra lines, because it's like some kind of accurate distances, and based on that, I measured, for example, getting 2 pixels on the image and then using the algorithm to calculate the on-ground distances. And since I have already like measured this on the ground, so based on that, I tuned my algorithm to have 10 centimeter error in all these areas that I have shown here. Let me bring the areas in these areas. So basically, I have parameters for this. If 2 points are here, I can get the pixel coordinates on of these 2 points, and then using the algorithm calculate the on-ground distances.
Yeah. Okay.
Yeah.
Cool. Yeah. Lots of manual annotations.
Yeah.
Thank you.
Thank you so much, Mashid. Let's move on to our next presenter.
Okay.
So our next presenter is Yige Hong. Yige, please share your slides and take it away. Yige, we can't hear you.
You're still muted.
You're still muted. It looks like you're muted on Zoom.
Okay, now can you hear me?
Yep.
So hello everyone, my name is Igor Hong and I'm from Carnegie Mellon University. My topic today is about sharp zero queuing bounds for multi-server jobs. So let's start with the motivation. So what I study is a queuing model that is motivated from a data center. A data center's operation involves serving a stream of job arrivals, and this process can be modeled as a queuing system, which consists of servers and jobs that arrive from time to time. By analyzing the queuing model, we can give predictions of the waiting time and find better policies. So what I consider in my work is a special type of job called multi-server jobs. A multi-server job is a type of job that occupies multiple servers during its service, as contrast to traditional queuing models where one job is only fit to one server. Examples of multi-server jobs can be computer programs that run on multiple CPU cores. The server need of a multi-server job can have huge variance. Like the statistic from Google, you can see the x-axis, the normalized CPU request vary from 1 to 100,000. So here the server need is just the number of servers required by a multi-server job. So therefore it is important to build a model that considers the effect of multi-server jobs on the performance of our queuing model. So here is our model. Our model consists of n servers, which are denoted by black cycles, and several types of jobs. Here I only draw 2 types of jobs. And the system dynamic is as follows. Take the red job as example. It arrives at a rate lambda1 following a Poisson arrival process. Then it enters the system and probably wait in the queue. After a while, a scheduling policy will put the job into service. And during service, it will occupy 2 servers simultaneously. And maybe after a while, it is put back to the queue again to make space for other jobs. After a job has received enough service, it will leave the system, and the service time will follow exponential distribution of rate mu1. During this process, the amount of time that a job spent in the queue is called the waiting time. Our freedom here is to design scheduling policy. How is that stable? The freedom here is to design scheduling policy that decides which job to serve as the policy, which is the default policy. It takes the job one by one, starting from the head of line, and put the job into servers until there's no enough servers available. Note that for any feasible policy, we cannot serve a multi-server job partially. For example, here, there are only 2 servers available, so we cannot serve another blue job, but we can serve another red job. Our objective is to understand the minimal achievable mean waiting time in steady state. Here, the W bar infinite is a notation for the mean waiting time, the random variable of waiting time in steady state. And we want to minimize over all possible scheduling policies. Similar models has been studied before by many people, and it appears that exact analysis has been hard. But things will be easier if we consider a larger system. In the paper of this year, they analyzed the queuing probability under a scaling regime with a large number of servers. Our work will study a similar scaling regime, but our objective will be the mean waiting time. So here is our scaling regime. We consider a large system scaling regime that captures the features that there are lots of servers and a huge arrival rate and probably a huge variance in the server need in the real data center. Technically, this means we want the number of servers n go to infinite, and we also want the arrival rate and server need to scale up with n. So how do they scale specifically? So we define 2 parameters. One is slack capacity delta, which is which intuitively means the expected number of idling servers. And the other parameter is the maximal server need, Lmax, which is just the maximal of the server need. We want the system parameters, the N, L, and the lambda to scale up in a way so that the slack capacity is of order is equal to N to the power of alpha, and the maximal server need is N to the power of gamma. So we want alpha to be less than 1, so that alpha and gamma to be less than 1. So the slack capacity and maximal server need are diminishing compared with the number of servers. And we also want the maximal server need to be smaller than the slack capacity. Under this scaling regime, we expect that under most of the reasonable scheduling policies, as n go to infinite, the mean waiting time should converge to 0. So the question is, what is the rate of convergence? The rate of convergence can depend on policies, and our analysis will be concerning the rate of convergence of mean waiting time of different scheduling policies. So now we come to my findings. So my first result is about the mean waiting time of the first come first serve policy. I first studied this policy because this is used a lot in practice. So we show that under first come first serve policy, the mean waiting time is of order n to the power of gamma minus alpha, where gamma is the exponent in the maximal server need and alpha is the exponent in the slack capacity. Because we have assumed that gamma is less than alpha, the mean waiting time is indeed diminishing when n goes to infinite. However, when alpha and gamma are close, the rate of convergence is pretty slow. So can we do better? Our next result gives a lower bound that no policy can go beyond. It shows that the mean waiting time should be at least n to the power of negative alpha. The proof involves using drift method and coupling with an infinite server system. We compare this lower bound with the previous mean waiting time of the first come first serve policy, and we see that there is a gap of n to the power of gamma. So this means the gap is pretty large when the maximal server need is large. So now comes the question that is it because the first come first serve policy is suboptimal or because the lower bound is not tight? So our next result show that the lower bound is indeed tight. It is achieved can be achieved by a priority policy. The priority policy is constructed as follows. We prioritize jobs with smallest server need. And this policy works preemptively, which means we can interrupt the jobs during the middle of their service. We show that under this priority policy, the mean waiting time is achieve the lower bound n to the power of negative alpha. So now comes the conclusion. So we have studied multi-server job model, and multi-server job model is important for analyzing the performance of data centers. And we have characterized the order of mean waiting time and found the optimal order. Moreover, from the theoretical analysis, it appears that the different scheduling policy can have very different performance, which means that scheduling does matters in such a model. We have used some novel proof techniques in our proofs. In particular, the lower bound proof will be interesting because and such kind of lower bound results are rare in literatures. And the possible future direction might be finding a non-preemptive policy that achieves the same lower bound. As we might notice, the current policy that achieves the lower bound is a preemptive policy, which means it must interrupt jobs during their service. This is not an attractive feature to implement. So it will be interesting if we can find a non-periodic policy that performs similarly, but do not require preemption. So this finishes my talk. Thank you.
All right, thank you, Yi. Questions? Nicholas.
Yes, thanks for the interesting talk. I have a question about a small question about the last theorem that you show. Is there any condition on gamma here, or can it be anything? And the second question that is related is like what happens when gamma is larger than alpha, meaning that when the job sizes are larger than can be larger than the stack, especially for first come first serve or here, like is the system unstable, or can you comment on that?
Okay, so in all the theorems, we assume gamma is less than alpha. And as for what happens when gamma is bigger than alpha, yeah, I think there will be difficult, even stability, there will be some difficulty to guarantee. So, but it will be interesting to study the case when gamma is bigger than alpha.
But that it can be some kind of a knapsack problem, or
yeah,
non-trivial.
Yeah, so the proof here relies on a kind of a property that no matter which order we schedule, as long as we put as much jobs into servers as possible, the system will be stable. But when the gamma is bigger than alpha, we may need to decide which set of job to put into service so that we can better utilize the servers, so that there will be not too much servers idling.
Okay, thank you.
Shailesh?
Hi, have you thought about the setting where jobs have multi-dimensional resource requirements, like they require some amount of CPU, some amount of disk memory, things like that? Like, can you extend this type of a study or analysis to that setting?
We haven't considered this in this paper. I think there has been some work on the multiple types of job, that is about virtual machine scheduling, and the current work are mainly about the stability. And probably we can try to extend our current analysis to that, to multi-dimensional resource requirements in the future.
Okay, thank you. We have time for one very quick question from.
Thanks, Eji, for the talk. My question is related to Nicholas' question. So, regarding stability, since the lower bound says that the mean waiting time scales is n to the power minus alpha, so it seems that it doesn't depend on gamma. But is the proof of lower bound assumes that gamma is less than alpha? Does the proof assume that?
Yes, the proof assumes gamma is less than alpha.
In the lower bound.
Yes.
Okay.
In the lower bound. Let me see. Yeah, I need to check that. I need to check that. I assume that's all the way through, but I'm not sure if it still holds if I remove it.
Okay. Thanks.
Thanks very much. And our last but not least speaker is Shrestha Puri from Imperial College London.
Hi everyone, I am Shrestha Puri, a PhD student at Imperial College London, and today I shall be presenting my work titled Split Place, Intelligent Placement of Split Neural Nets in Mobile Edge Environments. So let me first discuss the problem itself and why I find it particularly exciting. And as we all know, that in recent years, deep learning methods have become more or less ubiquitous in industry and academia. And modern deep learning models can solve some of the most complex pattern recognition problems today. But they usually come with several deployment level challenges. First being that they have massive demands for compute and storage resources, which makes deploying such neural networks challenging in specifically mobile edge computing platforms where these nodes are resource constrained. The next problem is of cost, and to deploy an upgraded AI model, typically tech giants like Amazon, Netflix, and Google need to completely revamp their infrastructures or upgrade their devices individually, which raises many sustainability concerns. And this has made the integration of massive neural network models with such resource constrained devices very challenging and expensive ordeal. So it is very important for us as computer scientists to be able to deploy high-end deep learning models within legacy infrastructures. Specifically, the problem arises as complete neural models with the input batch can seldom be accommodated in the random access memory or the RAM of edge devices. And this not only leads to memory contentions, but also compute and network contentions, particularly when these models are placed in a network attached storage. And to solve this, a promising solution is to split resource-hungry neural networks into lightweight, disjoint, smaller components. And in the literature, we find two such methods called layer and semantic splitting strategies, as shown in the figure. Layer-wise splitting divides the network into groups of consecutive layers for sequential processing, which makes it a bit easier to deploy. But layer splits require the intermediate results to be forwarded to the subsequent edge nodes and processing to be done sequentially, such that the final output, processed output, is sent back to the user. This inherently increases the overall turnaround time of this decision. On the other hand, semantic splitting divides the network into multiple disjoint groups that use different set of features with no connection among them in these different split models. And due to the limited information sharing among these different neural network fragments, the semantic splitting scheme usually gives lower accuracy in general. But it provides parallel task processing and hence lower inference times, more suitable for mission critical tasks like healthcare or surveillance. However, there are no intelligent algorithms in prior work that contextually decide which splitting strategy to use and how to place such modular splits to edge nodes to exploit the low latency of edge nodes as well as the high inference performance of deep neural networks, both in tandem. Before diving into the technical details, let me first state some assumptions we consider in our model. Firstly, we assume a scenario with multiple heterogeneous edge nodes in a master-slave fashion. We assume that the CPU, RAM, bandwidth, and disk capacities of each node are known in advance. And similarly, we can sample the resource consumption of each task in the environment at any time. Moreover, we consider that tasks include a batch of inputs that need to be processed by a deep neural network. And for task, a service level deadline is defined at the time the task is sent to the edge environment. Further, we assume that all tasks are received from an IoT layer, which includes sensors and actuators. And this is sent to the edge broker via the gateway devices. And the edge broker then decides which splitting strategy to use, as well as schedules these fragments to various edge nodes in the system. In terms of the workload, we divide the timeline into equal duration intervals and create workload tasks at the beginning of each scheduling interval as a batch. So there are two main components of split place, the decision module and the placement module. To decide the splitting strategy, we use multi-amp bandwidth based formulation. Multi-amp bandwidth is a problem formulation where a stateless agent is expected to take one of many decisions, with each decision leading to a different reward. And the objective of such an agent is to maximize the expected long-term reward in an execution. But in our case, the most important factors to consider when making a decision of whether to use layer or semantic splits are SLA deadline and the accuracy achieved for each input workload. And this is particularly characterized by the reward function as shown here, in which we consider both inference accuracy and the SLA violation rates averaged over all input workloads. So to do this, the idea is to maintain multi-amp bandwidths for two different contexts. First is when SLA is greater than the estimate of response time for a layer split decision. And second is when SLA is less than this estimate. The motivation behind using these two contexts is that in case of SLA deadline being lower than the execution time of a layer split decision, such a decision would more likely be to violate the SLA as a result, delivery being after the deadline. However, the exact time it takes to completely run such an execution, the layer split execution, is a priori unknown. And for each application type, we need to maintain estimates of the response times for the layer decision. That is the total turnaround time it takes for execution inference, as well as transferring the intermediate results from one node to another. Okay, so once we have the splitting decision for each input task, we can now create, say, Docker containers using pre-trained layer and semantic split neural networks corresponding to the application, of course. And we consider 3 dataset workloads as our application types: MNIST, Fashion MNIST, and CFAR100. Another point to note here is that as multi-amp bandwidth model is more or less agnostic to the placement engine we use, in this particular work, we extend a popular reinforcement learning based model, which is namely the asynchronous active predict or A3C scheduler. And we consider 50 Raspberry Pi like edge devices and 2 baseline methods. The first being bottleneck, which is based on model compression, which is nothing but network pruning to fit these neural networks into a resource constrained node. And the second is Gillis method, which uses an extension of layer splitting with a heuristic based early exit strategy. So these figures show that split place method is not only able to reach higher accuracies and average values of the reward function, but is also able to drastically reduce the fraction of SLA violations for each of the 3 workload types. And split place is able to achieve these results being within the 20% overhead bound, which is considered as the least, as the maximum overhead in many of the prior art. Even though we do not explicitly model the quality of service parameters like energy consumption and average response time, we are still able to reduce these by up to 6 and 40% respectively compared to the baselines. And this is primarily due to the formulation of the reward signal of the multi-amp bandwidth model and its intrinsic correlation with other metrics of interest like quality of service parameters. So to recap, this work proposed a novel framework, namely split place, to manage resource demanding neural models in edge environments by leveraging neural splitting techniques. And this allows split place to not only manage tasks to maintain high inference accuracy on an average, but also reduce SLA violation rates and achieve state-of-the-art QoS parameters. However, this is only a preliminary work with some limitations, and we are working on some other exciting directions as well. The first limitation of this work is that the current framework assumes model splits are fixed, but splitting configurations might need to be changed dynamically for more heterogeneous and non-stationary edge environments. Secondly, the current framework assumes, or I would say specifically the placement module is oblivious to the split decisions, even though we intrinsically add the multi-amp bandwidth reward to the A3C scheduler. But still, we are working on tuning the placement module to be split decision aware, to using it as a prior to optimize quality of service. And finally, the current model assumes that all neural networks are divisible into independent layers. And this may be hard for deep learning models like attention or recurrent neural networks. And we're exploring to integrate them as well in our framework. Thank you all for your kind attention. Please let me know if you have any questions.
Thank you. Do we have questions? Wena.
Yeah, so I have a question regarding the split decision. So is the decision just to decide which way of splitting you are going to use, or does it also include how you are going to place the different slices onto different devices? And the follow-up question will be how often would you switch between different decisions?
So we include both of these. The split decision part is one module, which is controlled by the multi-amp bandwidth based model, as I discussed. And the other part of this is the placement module, which is like an extension of the A3C scheduler using the reinforcement learning. So these are working both in an interactive dynamic, both to optimize each other. And the multi-amp bandwidth is independent of the placement module, which is placing these splits to these edge nodes, and the placement engine, which is the A3C scheduler, is independent of the multi-amp bandwidth model, but uses that reward intrinsically.
I see. So the multi-amp bandwidth is for like choosing between the two ways of splitting.
Exactly.
And how often do you will it switch between different decisions very often?
It depends on the workload characteristics and how dynamic and how non-stationary they are. For our particular experiments where we are using these different workloads with a Poisson-based distribution for creating these tasks, if we have a lot of random noise added to the data, then what we see particularly in this image is that the layer decision continuously changes and tries to adapt to the volatile model or the more volatile environment itself. And that is what makes it more or less robust to the underlying infrastructure, because the underpinning model itself is dynamic and tries to adapt to this system. So if there are a lot of volatility, a lot of dynamism in the model, then it tries to make these decisions different at each time, each scheduling interval. But if the model is more or less stable, it tries to maintain that decision for a long time so that the overheads of migrations are as low as possible.
Okay, great, thanks.
Shailesh?
Sorry, in the slide where you showed the two contexts for the two multi-amp bandits, could you explain like what is A there and how do you compute the estimate EA?
So you're mentioning this slide?
Yeah.
Okay, so this what is happening here is very, very straightforward. We cannot reduce the response time of the semantic split decision. What we can do is to reduce the response time when we are choosing a layer split decision by changing our decision to a semantic split, just because semantic split is usually faster. And that is why it is important that we estimate how much time it will take for a layer decision to execute. And that is what this EL here is. And if the SLA deadline is more than this response time estimate of the layer decision, then we have a higher probability of choosing one decision over the other. And when this SLA deadline is lower, then we have a higher probability of choosing the other decision, which is the layer decision here.
So if your workload dynamics are changing, then you have to continuously like revise your estimate. And
yeah, so not mentioned in the slide, but what we are using is some sort of an epsilon greedy based exploration strategy. And as I showed here earlier, and what we do is we try to minimize the epsilon using, say, an exponential decay based on a reward feedback. And if the reward, say, increases, in the bottom left figure, you can see that if the reward increases, then I try to reduce my epsilon, where epsilon is the probability of choosing an, say, a random choice for exploration purposes. And 1 minus epsilon is the probability of choosing the choice that is given by the multi-amp bandwidth model. So again, based on the dynamism or the volatility of the scenario or the underlying framework or the workloads, this reward-based feedback allows, and the epsilon greedy exploration allows the model to dynamically tune towards an optimal QoS.
thank you.
Okay, thank you to all of the speakers. We are out of time for the speaker portion. So for the judges, we actually can't do a breakout room because this is a webinar. So what I propose is we converge in the Gather Town. We can find a little private space like we did on Tuesday. And then for the contestants and anyone who wants to hang out here, we'll come back as soon as we've converged on a decision and we'll announce the winners.